Alright everyone, let's start section 3, Understanding Spectra. This is where astronomy gets really exciting because by looking at light, we can figure out almost everything about a star, its temperature, its motion, and even what it's made of. So let's break this down step by step. Now when we look at the spectrum of a star, the overall shape of the spectrum tells us its temperature. Just like a stove burner glows red when cooler and blue-white when hotter. And so stars follows the same rule. So the spectrum is basically a cosmic thermometer. And the spectrum also reveals motion. If the lines in the spectrum shift slightly toward the blue end, the star is moving toward us. And if they shift towards the red, it's moving away. So this is called the Doppler effect. The same thing you hear when a siren passes by and the pitch changes. But here we are applying it to light. We will learn more about it later. Okay? And finally, every element leaves its fingerprint in the spectrum. Hydrogen, helium, sodium, each produces lines at specific wavelengths. So by identifying those lines, we can tell exactly which elements are present in a star or a gas cloud, even though they are trillions of kilometers away. And it's not just stars. These same techniques applies to galaxies, planets and interstellar clouds. Basically, any place light passes through gas, we can use a spectra to decode what's happening there. Now here's a perfect example, the sun's spectrum. The colorful background you see is the continuous rainbow of light coming from the sun's hot face called the photosphere. But notice the dark lines crossing it. Those are absorption lines. They appear because atoms in the sun's cool atmosphere absorb specific photons, removing those exact colors from the spectrum. And each line corresponds to an element. For example, sodium produces two strong lines in the yellow part. So by studying these lines, we know the sun contains hydrogen, helium, sodium and many more elements. Over 90 have been identified. Alright, now that we know what information spectra can give us, the next step is to understand the different types of spectra: continuous, absorption and emission, and the physical conditions that create them. Now before we dive into each type of spectrum, let me introduce you to Kirchhoff's law of spectroscopy. So these laws explain why we see three different kinds of spectra: continuous, absorption and emission. Now the first law says a hot, dense object like a star surface, molten lava or even a heated filament in a light bulb produces a continuous spectrum. So this means all wavelengths of light are present with no interruptions. So according to Kirchhoff's first law, if you have something hot and dense like the sun's photosphere or a glowing wire in a bulb, the light spreads smoothly across all wavelengths. Now think about things you have seen glowing when heated. Lava is a great example, or even the burner on a stove when it's red hot. So these are continuous spectrum sources. And of course, the sun's visible surface gives us a continuous spectrum as well. So when that light is passed through a prism or diffraction grating, we see a smooth rainbow from red to violet. And there are no gaps or missing pieces, just one continuous band of color. And this is what makes it unique. There are no dark absorption lines or bright emission lines interrupting it, just an unbroken rainbow of light. And here's where physics come in. From this continuous spectrum, we can measure temperature. And by using Wien's law, the wavelength where the light is strongest tells us how hot the object is. For example, cooler stars peak in the red while hotter stars peak in the blue. So this image shows an illustration of a continuous spectrum. Notice how the colors blend smoothly with no breaks. This is exactly what Kirchhoff's first law predicts for a hot, dense source. Now that we have seen Kirchhoff's first law, the continuous spectrum from hot dense matter, let's move on to the next two laws. So Kirchhoff's second law says, if light from a hot dense source passes through a cooler transparent gas, then that gas absorbs specific wavelengths. So the result is an absorption spectrum, a rainbow with dark lines. And next, the Kirchhoff's third law is the reverse. A hot, low density gas emits light only at specific wavelengths. So this produces an emission spectrum, bright lines on a dark background. And these two layers are really the keys to understanding how we read the fingerprints of atoms in space. So let's briefly discuss each law. Alright? Now imagine starlight shining outwards. As that light leaves the hot dense photosphere, it passes through cooler gas in the star's outer layers. So the atoms in those gases absorb very specific photons. And that absorption shows up as dark lines in the rainbow spectrum. And each dark line corresponds to one precise wavelength of light that's missing, because the atoms store those photons. And here's the powerful part. Those missing lines tells us exactly what elements are in the gas. For example, dark hydrogen lines or sodium lines in the sun's spectrum shows us that those elements are present. So here's the illustration. Notice the continuous rainbow background and those thin dark lines crossing it. So those lines are the fingerprints of atoms in the gas. And without them, we would have no way of knowing what stars are made of. Alright, now let's flip the situation. Instead of light passing through the gas, imagine we are looking straight at the gas itself, like a glowing nebula. So when atoms in that gas get excited, they release photons at the same exact wavelengths they would normally absorb. Therefore, instead of dark gaps in a rainbow, we see bright, sharp lines on a black background. And these are called emission lines. Now notice something neat. The wavelength of these emission lines match the absorption lines, like this. So it's the same atomic fingerprint, just seen in reverse. So astronomers see this by pointing a telescope directly at a glowing gas cloud or by blocking out background starlight. And that way, only the gas's own emission lines are visible. So here you can see bright colored stripes against black. And each stripe is one photon energy level that the gas atoms can emit. Again, the atomic fingerprint. So Kirchhoff's second and third laws gives us the dark line absorption spectra and bright line emission spectra. And together with the continuous spectrum from law 1, these three explains every type of spectrum we see in astronomy. So in practice, they let us decode the light from stars, galaxies and nebula, figuring out temperature, motion and composition just by reading these spectral lines. Okay, so now we know stars and gases produce absorption and emission lines. But the big question is, why do atoms only absorb or emit certain wavelengths? And the answer comes from the structure of the atom. Because remember, electrons can only occupy certain energy levels. So when they jump between these levels, they either absorb or emit a photon. And that's photon's wavelength. Its color depends on the size of the jump. So think of the electrons are living on a fixed floors of a building. They can't stand between floors. And if an electron goes up a floor, it must absorb a photon. And if it drops down, it releases a photon. So this explains why we see sharp, exact lines in spectra. Only certain jumps are allowed. And the color of the photon is determined by the energy difference between those flows. A big jump gives a short wavelength, high energy photon like UV, and a small jump gives a long wavelength photon like red light. Now let's look at the hydrogen atom, the simplest atom, because it has one electron, so we can clearly see its series of transitions. Here the arrow mark electron transitions. Downward arrow mean emission, and remember, the bigger the jump, the higher the photon's energy. Alright, when electrons drop to the ground level, n equals 1, the photons are in the ultraviolet. So we can't see this with our eyes, and we call this Lyman series. Next, when electrons drop to level 2, n equal 2, those photons are in the visible range, red, blues and violets. So these are called the Balmer lines. They are the only hydrogen lines we can see directly because they are in the visible region, right? And next is Paschen series. They occurs when electrons drop to the third level, n equals 3 level. And the photons are infrared, so invisible to us, but detectable with infrared telescopes. And this is why hydrogen's fingerprint in visible light is the Balmer series. Every other sets of lines, Lyman, Paschen, are beyond, requires special instruments to detect. Now one of the most famous is the Balmer alpha line at 656.3 nanometers. It appears as a deep red line in hydrogen spectrum, and astronomers use it all the time to study stars and galaxies. Now here's something neat. When a whole cloud of hydrogen gas in space is excited, all the Balmer lines are emitted together, and to our eyes that mixture looks like a purple pink glow, which is why emission nebula often look pink in astrophotography. So spectral lines are nothing more than electrons jumping between energy levels, and that's why each element has its own unique fingerprint. No two atoms have the exact same set of allowed jumps. Now so far we have looked at spectra as colorful rainbows with bright or dark lines, and that's a great way to introduce the idea. But modern astronomy doesn't just look at pretty rainbows. Instead, we record spectra digitally and represent them as graphs of intensity versus wavelengths. So this makes it much easier to measure and compare details. Instead of qualitative details, we get quantitative details. So here's what that looks like. Instead of showing color bands, we plot wavelengths across the bottom, the x-axis, and the brightness or intensity going up the side, the y-axis. Now see, in this stellar spectrum graph, the smooth curve shows how much light comes at each wavelength. And where the star is bright, the curve is high. And where less light comes through, the curve dips downward. So this is the modern way astronomers actually work with the spectra. So those dark absorption lines we saw earlier now appear as dips, sudden drops in intensity at exact wavelengths. Now what about emission lines? Instead of dips, they show up as sharp peaks above the baseline because the gas is giving off extra light there. So this method is much more powerful than just looking at rainbow bands because the graph shows line shapes and depths very precisely, and that tells us things like pressure, motion and even rotation in star's atmosphere. And because it's quantitative, we can compare two stars or gas clouds directly. For example, if one hydrogen line dips deeper than the other, it means more hydrogen along that line of sight. So the big takeaway is this. Dark lines in the rainbow spectrum become dips in the graph, bright lines becomes peaks. So it's two ways of looking at the same phenomenon. So now you can see, even though the rainbow version is more visually appealing, the graph version gives astronomers the precision needed to analyze stars and galaxies in detail. Alright, next let's see exactly what information astronomers can pull out of these spectral lines. Now, Kirchhoff's three laws can feel abstract when we only talk about stars and nebula. So, let's imagine an astronaut observing something more familiar, a lava flow on Earth. So, lava gives us the perfect everyday demonstration of all three spectral laws. First, the lava itself is a hot, dense object. So, according to Kirchhoff's first law, it produces a continuous spectrum, a smooth rainbow of colors. And that's because hot dense matter emits light at all wavelengths. Remember, and this is also what we call as black body radiation. And the brightest color or peak wavelength depends on temperature. So using Wien's law, we can measure lava's temperature from its spectrum. And that's the same way we measure the temperature of stars. Now imagine the astronauts look through the thin cooler gas above the lava. So now Kirchhoff's second law kicks in. The light from the hot lava passes through the gas and the gas atoms absorb very specific wavelengths. So they reveal the combustion of the gas floating above the lava, just like in star's atmosphere. And finally, if the astronaut blocks out the lava and looks only at the glowing gas itself, Kirchhoff's third law applies. So now the gas doesn't give a full rainbow. It only emits bright lines on a dark background. And that's the atom's unique fingerprint, no matter how you look at it. So this lava example shows all three Kirchhoff's law in one scene. Lava itself gives continuous spectrum, lava plus gas gives absorption spectrum, and gas alone gives emission spectrum. And the same principle applies to stars, nebula, and galaxies. So that's how astronomers use spectra to decode the universe. Alright, now that we know how spectra are formed and how to read absorption and emission lines, let's see how astronomers use those lines to figure out what stars and gas clouds are made of. So spectral lines act like fingerprints for elements, and each element absorbs or emit light at very specific wavelengths. Let's take an example. For example, the sun's spectrum has dark lines at 589.0 and 589.6 nanometers. And only sodium atoms can absorb light at these wavelengths. So over 90 elements have been identified in the sun using this method. That's amazing. We can tell what stars are made of just by looking at light. Now here's the sun's spectrum. Notice the bright rainbow background. That's continuous light from the photosphere. And the thin dark line shows light absorbed by atoms in the sun's atmosphere. So each line tells us exactly which element is there. Now be careful. If a line is missing, it doesn't mean the element is not there. It might just be that the star is too cool or too hot to excite those specific transitions. For example, the sun is mostly hydrogen, but its warm lines are surprisingly weak. That's because the sun's temperature is not high enough to produce strong visible hydrogen absorption. And here's an interstellar cloud instead. The emission lines from hydrogen, nitrogen, and oxygen are all bright. So comparing different objects lets astronomers figure out chemical composition under different conditions. Now on average, stars and most visible matter in the universe have a similar composition. 90% hydrogen, 9% helium, and trace amounts of heavier elements. So knowing these abundances is crucial for understanding stellar evolution, how stars live and die, and the history of the cosmos. And even planetary bodies can study it this way. For example, Titan's surface spectrum was measured by the hydrogen probe in the near infrared. So by analyzing absorption features, scientists can determine chemical composition remotely. So by carefully studying absorption and emission lines, astronomers can decode the chemistry of stars, nebula and planets. How amazing, right? Right. Now that we have learned how to read spectra, we can also use them to measure motion, not just the temperature and composition. So we can measure how fast a star or gas cloud is moving toward or away from us. And this is all thanks to the Doppler effect, which you have experienced in everyday life with sound. First, let's learn briefly about the Doppler effect. Now imagine a train approaching you with its horn blaring, and the sound waves are compressed. So the horn's pitch sounds higher than if the train was standing still. And once the train passes and moves away, the waves stretch out and the pitch drops. So here's the illustration. Notice the waves are closer together as the train approaches. That's the higher frequency. And when the train moves away, the waves are farther apart, producing a lower frequency. And the same principle works with light. If a star is moving towards us, its light waves are compressed. That means blue shift, which gives shorter wavelength. And if the star is moving away, its light waves stretch, meaning red shift, which gives longer wavelengths. So see the light waves in the diagram. When the source moves towards the observer, the peaks are closer together. That's blue shift. And when it moves away, the peaks are farther apart, and that's red shift. Now it's important to remember red and blue here don't mean the star literally looks red or blue. These terms just indicate the direction of motion relative to us, red shift or blue shift. And this effect is not just for the visible light. It applies to the entire electromagnetic spectrum, X-rays, radio waves, infrared and visible light. So any wave phenomenon shows the Doppler effect. So the Doppler effect gives us a way to measure radial velocities, the motion of stars and galaxies along our line of sight. Alright, now that we understand the Doppler effect in general, let's see how it works in real astronomy. So astronomers measure tiny shifts in spectral lines to determine the motion of stars along our line of sight. And this motion is called radial velocity. Now let's take the star Arcturus. So observations at different times of year show tiny shifts in its spectral lines. In winter, blue shift because Earth is moving towards Arcturus, and in summer, red shift because Earth is moving away. Now here's the actual spectra. See how the absorption lines are slightly shifted left in winter, that's blue shift, and right in summer, that's red shift. So these tiny shifts let astronomers measure the star's motion relative to Earth. Now here's an important point. The Doppler effect only measures motion toward or away from us. And that's the radial velocity labeled as VR. So any motion perpendicular to our line of sight, side-to-side motion, does not cause a shift and cannot be detected with this method. Okay, let's think of a police radar gun. It measures the speed of a car coming straight at or away from the radar. But it can't measure how fast the car is moving sideways along the road. Now in this diagram A, it shows the radar example and B shows a star moving through space. So only the component of velocity along our line of sight produces a Doppler shift, and the sideway motion is invisible to this method. So by carefully measuring tiny shifts in spectral lines, astronomers can calculate radio velocities of stars, planets and galaxies. How amazing, right? And that's all thanks to Doppler. Okay, now that we understand how Doppler shifts indicate motion, we can calculate the radial velocity of a star using a simple formula. And this equation relates the change in wavelength of spectral line to the velocity of the object along our line of sight. So this is a simple proportion. The fractional change in wavelength equals the fraction of the speed of light at which the object is moving along the line of sight. And positive delta lambda. If delta lambda is greater than 0, it means redshifted. So the object is receding. And negative delta lambda. If delta lambda is less than 0, if it's a negative value, it means blue shift. That means the object is approaching. So this works for velocities much less than the speed of light, which is true for most stars in our galaxy. Now here VR tells us how fast the star or gas cloud is moving toward or away, which is the radial velocity. And C is the speed of light, which is a constant. And its value is 3 times 10 to the power 5 kilometers per second. Or in meters per second, it is 3 times 10 to the power 8, right? And lambda naught is the wavelength you would measure if the star were stationary, not moving. Delta lambda is the tiny shift we actually observe in the star's spectrum. So this equation is the key tool astronomers use to turn a tiny shift in a spectral line into a real velocity in kilometers per second. Alright, now let's put the Doppler formula into practice. So here's the question. A spectral line has a laboratory wavelength of 600 nanometer. But in a star's spectrum, it is observed as 600.1 nanometer. So what is the radial velocity of the star relative to Earth? Now do you think the star is moving toward or away from us? What do you think? Let's find out. First we need to calculate delta lambda, which is the change in wavelength. And we know the observed wavelength lambda is 600.1 nanometer. And the laboratory wavelength lambda naught is 600 nanometer. So what is delta lambda? It is just lambda minus lambda naught. So subtracting these two values we get delta lambda equals to 0.10 nanometer. Now here naught is the positive sign. Delta lambda is greater than 0, right? So this already tells us the star is moving away from us, which is a redshift, right? Now to calculate the radial velocity, let's plug in delta lambda and lambda naught into the Doppler formula. So we just calculated delta lambda and lambda naught is given here, and c is just the speed of light. So we know all these three terms. Therefore we can calculate the VR, radial velocity, right? So if you plug in all the numerical values, delta lambda is 0.1 nanometer and lambda naught is 600 nanometer and c is 3 times 10 to the power 5 kilometers per second. So if you do the calculation, you can get radial velocity VR is about 50 kilometers per second. So this is the speed at which the star is moving away from us along the line of sight. Now here delta lambda is greater than 0. So in this example, the star is moving away from Earth at 50 kilometers per second, right? Now what if delta lambda is less than 0? That means blue shift. Then the star approaching towards us. So this example shows how a tiny change in wavelength, barely 0.1 nanometer, can tell us exactly how fast a star is moving. Alright, now with this example, we conclude section 3 and the chapter. So far in this section, we have learned how spectral reveal important information about stars, including their temperature, motion and chemical composition, and how astronomers use absorption and emission lines, atomic transition and the Doppler effect to study stars, planets and gas clouds. So let's move on to chapter summary. Alright, now let's start by reminding ourselves what atoms are. Every atom has a nucleus with protons and neutrons, an electron cloud orbiting around it. And the number of protons tells us which element we are looking at. And if you change the number of neutrons, you get isotopes. Next, if electrons are lost or gained, the atoms becomes an ion. Pretty neat, right? And when atoms join together, they form molecules, the building blocks of everything around us. Now in the second section, we saw how atoms interact with light. Electrons live in energy levels. They can jump up when they absorb energy and fall back down by giving off light. And temperature also plays a big role. It tells us how much particles are jiggling around. And when objects get really hot, they glow. And that glow is thermal radiation. And we can use Stefan Boltzmann and Wien's law to figure out how hot stars are just from their brightness and color. Isn't it cool that starlight tells us temperature? Alright, finally we explored spectra. Remember Kirchhoff's laws. A hot dense object gives us a continuous rainbow. A thin gas gives bright emission lines. And if light passes through a cool gas, we see dark absorption lines. So each element has its own unique fingerprint of lines. So we can tell what stars are made of. Next, the Doppler effect let us measure motion. A blue shift means a star is coming toward us, and a red shift means it's moving away. So spectra are like nature's secret code for composition and motion. Alright, now with this we wrap up chapter 7. So be sure to go through the practice questions. They will really help lock in these ideas before we move on to the next chapter.